I don't know. I feel like the internet is not that stable today. So remote students, if it's really slow and flaky, let me know. If that's going to remain the case, we'll then have to move to the wired Ethernet connection. Can the class hear me? Okay, good. Okay, let's go ahead and start. The announcement for this week is very straightforward. Um, the only thing that's doing is just 2 quizzes, okay? And then enjoy the spring break. Now let's move to the slides. So this is where we ended up with. And by the way, remote students, you might see me walking through the podium and back. So I have another camera here so that you guys can see me walking, because I do feel a little bit uncomfortable being leashed to the podium. Okay, so I'm a little bit more dynamic. That might help you concentrate a little bit easier. I don't know. I don't know about you as well. I seem to think a little bit better when I'm walking. Good. So this is where we ended up with cookies. Not the Oreo cookie, but the HTTP cookies. So cookie is the thing that help HTTP to maintain states. Okay, the way it works is this. We're here with the browser, browsing the web, say, so we are clients. So there's a certain disk space, usually configured by the browser. So you could actually change that, okay? Change which folder exactly that you're storing these cookie files. So somewhere in the disk space, you have this cookie file. And that cookie files gets updated and updated and updated, okay? So you might have this eBay A734 to begin with, okay? And today we are accessing a server, Amazon.com. Okay, so what happened there is when we send the web request, 1 second. We send the web request, okay, to Amazon.com. The server here creates, okay, an ID for you. Okay, and this is actually whatever the server feels like giving you. So 1678 is just an example. So now we are Amazon 1678. So correspondingly, the backend database of Amazon.com will then create an entry. Okay. In the object you requested, okay, that response will then, of course, carrying the web page. But in addition, there's a header line called setCookie. So this is when you add the Amazon 167A into your cookie file. So for the subsequent request, in the header line, there will be a cookie 167A. This is again for Amazon.com to identify, oh, you are that user, 1678. Welcome back. Okay. And so the backend database might actually fetch your previous browsing history. Okay. And then, for example, suggest what's the next item that might be related to your current search. Okay. So in that response back to the client, there could be these additional advertisements coming in. So what happened here is, well, you might finish browsing, but 1 week later, you come again with your cookie files being like this. When you send a request to Amazon.com again, you already send the request carrying this header line, cookie 167A. Amazon.com here will say, hey, welcome back again. You know what? You're now looking for smartphones. Let me recommend you smartphone cases. And sometimes if you are purchasing smartphone a week before, that is iPhone 8, for example, then they recommend you the cases for iPhone 8. So that's how you find, hey, how do you know Amazon.com or PC Home? How do you know what I was looking for? Yeah, they get your history here. You see, having these cookies, it's somewhat convenient because to a certain degree, the server knows who you are, uniquely. So for example, if you don't want to log in and yet you want to shop, right? One thing is that you click into an item, right, and you close the transaction immediately. But if you want to buy multiple items without cookies, then you have to do it multiple times. With the cookie, they will know that, oh, you are 167A. Okay, all these 3 items, you pay with 1 credit card, and you are 167A. And recommendations that I don't have to repeat, you heard. So in a way, there are these user session states, not necessarily your private information, such as your birthday, your credit card number, but there's a unique ID there that the server can decide who you are. But then on the downside, do you worry having lots of these cookies? If you go to the same site, shopping all the time, well, right, the server knows entirely your life, pretty much, right? You wear a certain brand name of T-shirt, you wear certain glasses, you use a specific type of laptops. They can do a lot of things with all these data. So privacy was a serious concern. And nowadays, you go to websites, you often see the website pops up. This cookie is required. Would you permit? What do you do? There are usually options saying you can configure. But did you bother configuring the cookies? Oh, you did? Okay, Samuel, you're smart. If you say permit, that means you permit everything. So there's one time I need to tell you. I was no longer interested in keeping a car myself. So there's this iRent system there. We can timeshare cars. I just need a car to go to Costco. Otherwise, the metro system is so convenient. So Costco, I have many stuff I need to carry home. There's no way, right? I take public transportation with it. So I Google iRent, and then the next day I receive a phone call from 和运租车. Oh boy, oh boy. I really don't need them to know all that much about myself, but they're really good these days. So yeah, cookie, privacy concern. Okay, so advantages, and there's one but very big disadvantage. But bottom line, cookie, there is a way to allow HTTP to retain states about the users. If you recall, HTTP is what? A stateless protocol. Okay, that makes it very simple. Memory requirement very low, but it also is a little bit inconvenient, okay, without being able to keep the user state. So cookie there is some addition to compromise the situation, okay, to provide us a compromise. Okay, so HTTP messages now can carry some state with the cookies, with the set cookie line. All right, and the states are maintained at the protocol endpoints, receiver and sender. Now, we move into another topic, the last topic of HTTP. It's called the cache. There are two kinds of caching we do. Okay. First is the straightforward one, called the local cache. Okay. Technically speaking, it's called the, I see myself showing both on, oh no, I think the iPhone video is frozen. No, it's just a little bit slow. Interesting. Guys, you know, students, it seems that the iPhone video part is going really slow. It's still 10 minutes ago. Interesting. Well, anyway, I have to debug that later. But local cache. Technically speaking, it's called the conditional get. Okay. If you recall, get is the kind of request. Okay, that's what? Asking for a web object, downloading a web object. Okay, so conditional get is the special type of get. Okay. So client is here, server is here. A client can issue a conditional get request. Okay, and the way it works is this. Let's just look at the animation. It'll be easier to understand. So in that request, carry a very special header line. If dash modify dash since, and then providing the date, okay, of the object, of the same object that the client has previously downloaded, okay, and this date is the date that the object is previously downloaded, and that is kept in the client's hard disk, local cache. Okay. Server here will check whether that object, that web page here, okay, has been changed or not since the state. If it's not changed after this, what does that mean? That object here and the object here cached locally are the same, isn't it? Is there a need for the server to send the object back again? No need. Therefore, the HTTP response will be just saying this in the header line, in the status line. It's 304, non-modified, okay? And therefore, no data, okay, is being appended to the response message. What's nice about this is that, hey, you save some network bandwidth here. Now, the other condition, of course, is send a request if modified since the day, and the object has been modified. What would the server do here? Okay, to be precise, to be correct. Okay, send back the object, send back the data. So the status code is now 200 OK. All right, so at the client side, we specify the date of the copy being cached, okay, previously. So adding this line in the request message. Server check the date. Okay. If it has not been changed at all, then contain no object, and the return response carry the status line. Okay, so do not send object if the cache is okay, up to date. So there is no object transmission. We save some link bandwidth. So that was the easy form of cache. Okay, the local cache. Now we go to this other form. So instead of keeping copies of these web objects on local hard disk, Let's keep it in a special machine in the middle of the network. And the way it works is also simpler if you look at the animation. Client number 1 here, requesting a web page. Okay. Client number 1 here, okay, having already set a proxy server. So the browser here is preset to go to a proxy server. So web requests will all just go to the proxy server instead of going to the server, the particular server that we are requesting the objects from. So you see, requests going to the proxy server. Now, proxy server not having that object locally on its hard disk would then forward the request to the origin server, okay, to the server originally keeping the object. Server here respond to the proxy server with the object. That object gets cached here in the proxy server, in the middle of the network. And proxy server sends a copy of that object back to the original client. Do you like that? What do you think? Would the delay be longer or shorter? Right? Assume that there's a certain triangular relationship, right? Direct request from client to origin server seems to be faster. Why? Think. Client number 2, asking for the same object. And client number 2 here is nearby the client. And both of these clients are probably taking the same course. Okay, they often refer to the same pages. So client number 2 here, request for the object. That goes to the proxy server. And you know what? Proxy server has the object. Therefore, quickly respond with the object. And client here does not need to go all the way to the origin server, isn't it? So what are we saving here? We're actually saving this part of the delay and help this part of the network to conserve some network bandwidth. And think about this. If we have many of these clients sharing interests locally nearby the proxy server, right? It's not bad at all to set up such a cache there in the network. So that's the idea of proxy server. Okay. So you see that proxy server there act as both the client and the server. Serving the local users as a client, fetching content from the remote server. And such a cache or such a proxy server is typically set by an ISP. So for example, NTU sets up one of those proxy servers for us. For example, your home residential ISPs might set up such a proxy server nearby. Okay. Now, why web caching? You see that, hey, we save a little bit, right, for each of the clients that share same interest. Let me use a concrete example to walk you through so that you are better convinced. So here's the example. So we do have the internet, lots of servers out there, and we're here, okay, tiny little clients, okay, looking to fetch web pages down here. The configuration is that between the institutional network and the rest of the internet, so this is the institutional router, so this is the router that connects the institution to the rest of the internet. We have only a very low, okay, low bandwidth access link, 1.54. Okay. Let's assume, okay, each of the object, on average, 100 kilobits. And we are requesting, okay, from browsers, 15 objects per second, right? So the daemon here, user, for objects here, is 15 multiply 100K. And that is 1.5 megabits per second. So the data rate coming down this way, 1.5 megabits per second. Let's assume that the round trip time from the institutional router to the servers and back are all 2 seconds. Okay. Assume that it's a horrible public internet. Round trip time, 2 seconds. And now excess bandwidth is 1.54. Let's try to estimate the delay of getting these objects. In terms of local LAN delay, hey, local LAN is 1 gigabits per second, okay, LAN. And 1.5 megabits is really, really low. So the delay for the LAN part, delay component for LAN part, very small, okay, milliseconds. For access link part, how much? Well, the utilization, 1.5 megabits over 1.54 megabits access link. That's really high, right? What would the delay be like, the access delay be like? It's actually very long. Okay? It can go up to minutes depending on the time, okay, you are looking for the data. Internet delay, which is this part, we already set it to 2 seconds. So internet part, access part, and the local subnet part. So altogether, the delay scale is at the minutes. Okay. Well, to explain the minutes, let me bring up the slide that we've seen before. Here, queuing delay. What we are having here is utilization close to 1, isn't it? 99%. So delay goes really large, approaching infinity. So that's why I'm putting minutes there, okay, on the side. Now let's consider this other case. So it seems that this is the problem, isn't it? Why don't we just change it to higher bandwidth, okay, 154, 100 times higher, okay? Now link utilization is much lower, and then the delay for this component much lower, okay? Milliseconds typically, then great. About 2 point something millisecond. Would this be nice? Nice. Well, there's one catch. How easy to change this, okay, from low bandwidth to 100 times higher? It's not cheap, okay? It is not cheap. Therefore, instead, okay, let's keep this the same. Just add a server machine, okay, large hard disk space. And let's see. Object size the same, downloading speed the same, internet access delay the same, okay, access link rate the same, LAN utilization the same. Access link utilization, total delay? Well, let's compute that. But what we know is that adding a server machine here, it's relatively cheap these days. I think 30K NT dollars give you a really, really nice machine already, because server doesn't need to have monitors, so it's very cheap. So let's compute access link utilization and the total delay. The reason that this is a little bit tricky is because, hey, so this maintain caches. This is the proxy server. Request will go here and see if there's a hit, okay? If that object this guy is looking for is here. So the delay depends on what? The hit rate here. Okay, let's assume a hit rate that's 40%. 40% of the objects these guys are requesting, we get to find them in the cache. And 60% missing, therefore, the proxy server needs to request the object through the internet. Then you see, access link utilization, what, is 60% of 1.54, isn't it? That is, let me see. Yeah, only 58% utilization. So 60% link utilization, is that? Sorry, I think I was, yeah, it is right. This is the data rate, and this is the link capacity, so this is correct. So 58% utilization. The total delay, therefore, is 60% of the time delay goes to the origin server and back. 40% only locally. So 60% of only 2 something second. Okay, so this is definitely not 99%, so the delay, the queuing component goes to minutes. It's limited by the round trip delay here, 2 seconds. And then 40%, very, very small, microseconds. So overall, the average delay is only 1.2 seconds. Is this better or the second solution better? I mean, the first solution, this is the second one. This is even better than, okay, enlarging the access links bandwidth, isn't it? So it's better and cheaper. That's why we do proxy servers. Okay. It's to reduce the response time and also reduce traffic, reduce cost. Okay. Now, one very minor, but to some people very important benefit is this. Now with these proxy servers around, okay, contents are cached. So for those content providers that are poor, they don't have money to supply that much upload bandwidth. The users can still access their content fine. So this is mainly for example, NGO companies. Okay. So to one extreme, okay, P2P file sharing is partly to enable this. Content sharing by the poor users, poor providers. Good, so we've just concluded HTTP and we move now next to the FTP. So this is the first application, World Wide Web. Okay, HTTP is the supporting application layer protocol. FTP File Transfer. Okay, this is the second one. Well, in fact, you guys are all familiar with it. Okay, client here, server here. Server meant to have a large hard disk. Client here might have a relatively smaller hard disk. Essentially, a lot of times we are uploading files to FTP server or downloading files from the FTP server. So what I'm drawing here is that the requesting downloading part, that's the client, FTP client. But there's, just like the web browser, right? So there's an HTTP client part, but there's also the browser rendering, displaying part, the user interface part. So FTP similarly also has that. Okay, you see that in FileZilla, right? So nice, pretty graphical user interface. So what it does is simply transfer files. Client is the one initiating transfer, whether it's downloading or uploading. Server is always the one that's remote. And it's using port 21, and FTP uses also TCP, okay, as the underlying protocol. So you see that the communication model, client-server, architecture also similar, right? The client sends requests, server sends response, okay, something like that. And underlying protocol, TCP, and it's using port 20. But allow me to be a little bit more precise about FTP. The communication, the network structure is the same, but communication not quite the same. You see, client here, okay, usually will need to authorize itself with the server. So username and password authorization is done through this thing, a control connection. And then once you log in, right, you might move around, okay, in the remote hard disk, okay, from one direct to another. And you might check the file names. That is also going through the control connection. Only when you click on a file or double click on the file and starting the file transfer, then there's a separate connection, the data connection being created. And that's where the files are being transmitted. When the transfer is done, this data connection is closed. If you click on another file, another data connection started. When that transfer completes, the data connection closes. So, control connection, data connection. So, server, like this, opens up another TCP connection and separating control messages, separating comments from the actual data. That is called the out-of-band communication. If you recall in HTTP, the commands like get, post, and the data, do they go on the same TCP connection? The status line and the data, do they go on the same connection? Request message, response messages go on the same connection, isn't it? But here in FTP, they go on two separate connections. Control connection 21, the data connection 20. And the data connection goes on and off and on and off. Okay, if the transmission is completed, close, start again. Something else that's a little bit different in FTP is this. FTP is stateful. FTP actually keeps the status of the user. Okay. Unlike HTTP being stateless. So this is just to give you an idea of how the comments look like. You see, again, in FTP, just like HTTP, they are all readable text, ASCII text. So user, and then the username here is the command to ask the server, this is my username. PASS and the password. Okay, so these two are for the server to authorize the user. List is the command to show the list of the files in the directory. Retrieve is to retrieve a particular file, download a particular file like get. Store pushes a file to the server, puts. Okay. So these are some of the status code and phrases that the server might return to the client. For example, username okay. So it might be user and Polly Huang here, and then the server says 331 username okay, and then ask for password. And then here, client sends password. Right? So it's following a specific format. So looking in a very similar way as the HTTP requests. All right, let's do a short discussion here. Compare HTTP and FTP. What do you think? Which one is client-server model? Those who say HTTP, raise your hand. One hand, hesitating hand. Who says FTP is a client-server model? 2, 3, oh, more hands, good. Right. Both of them, client-server model. Which one of them use TCP socket as the underlying service? Too simple? Okay, how many says both? Messages in readable form? Both. Comments and data sent together? Yeah, very good. HTTP. FTP send them through separate channels. Which one is stateless? HTTP, I heard you. Okay. Very good. Now, let's move on to yet another application, email. Okay. So this is email's network structure. There are 3 major components. One is the user agent. So they are these guys, user agent, okay, at the outskirt. Second component, these guys, okay, big rectangle boxes, okay, the mail servers. third component. The third component is not physical. It's the protocol running between the mail servers. Okay, you hear keyword server. Okay, you are right. In email transmission, okay, the model is also client server. So allow me to explain a little bit more. What are these user agents? So they are essentially the mail readers. So it could be the Outlook, Thunderbird, or your iPhone's mail client. Nowadays, we use web browsers to read emails most. Okay, so web browser is also a user agent. Okay, so these are the applications we use to compose, edit, reading emails. But sending, receiving of the emails are all on the servers. Okay, so we only use these guys to re-edit. So the main roles are these, okay, at the servers. So inside the mail server, okay, each user is reserved with some space. First component is called the mailbox. Okay, so it contains all the incoming messages for that user. So these are the yellow part, user mailbox. So incoming emails will all get queued up here, waiting until the user accesses them. There's another space, okay, message queue, the green part here. So this is where the outgoing emails are kept temporarily, okay, before they can be pushed to the receiving mail server. And then running on top of space, the mechanism is called SMTP. Okay, it's running between the mail servers. Okay. What's a little bit strange here? Pay attention. Okay, the client of SMTP is the sending mail server. The server there is the receiving mail server. Okay, so if I'm here writing an email, my email server, usually my email server is nearby. Getting the email will push it into the green queue. And this server here will try to establish a connection to the receiving mail server. Let's suppose it's here. So once that is established, then the email coming out of the green queue will come in here to the yellow queue, okay, for the destination, for the email receiver. So are you confused? The client here is the sending mail server. Wait, the server is also a client. What does that mean? The whole email system, okay, works in two levels of hierarchy. There's one between the user agent and the local mail server. Agent here is the client. Okay. Server here is to provide the service, storing outgoing email and keeping the incoming email. Okay. So this is called the email access service. Okay. It's not email forwarding, sending service. It's just email access. Now, among the SMTP entities, now this is the real email service. Okay. Sending emails from the source to the destination. So at this level, who's the client, who's the server? The sending one is the client, the receiving one is the server. Okay, because email is always coming from a sender. Okay, so sender is the one looking for a service, okay, a delivery service. All right. So each of these is called a server because they allow the user agents to access, providing the access service. But this guy here being the receiving server, it's the server at the SMTP level for this client. All right. Oh, you begin to see, hey, one of these internet services we use is no longer in a flat hierarchy. Email service now, you see two levels of hierarchy. Again, TCP running at 25. So underlying protocol is TCP. Data direct transfer between the sending server and the receiving server. And the message actually looks pretty much the same as all these other protocols we see. At the beginning, there's like a connection establishment, handshaking, greeting, and then real data begin to get transferred, and then closing. Comments are all readable ASCII. In the response, you see status code and status phrase. And to walk you through the entire process, okay, I'm using an example. Alice sending email to Bob. So Alice will use the user agent to compose a message and send it to bob@someschool.edu. So right here, step number 1. Alice's UA then send the message to her mail server right here. Okay, so step number 2. So message will be queued here in the green part. Step number 3, the client side then start SMTP and connects to the receiving server. Step number 4, send the email through the TCP connection. Step number 5, that message gets into Bob's incoming queue. Step number 6, Bob's come and start the user agent and access the email in the inbox. Quite straightforward. Okay. So we can try to telnet to a mail server and see if we get these weird messages. Okay. So all these are text-based. So if one look into the content of these messages, you see very clearly. Once we connect to a receiving server here will say 220, okay, hamburger.edu. So this is saying that, hey, I'm connected, and my host name is hamburger.edu. The sending server says, hello, I am crepus.fr. And then receiving end says 250. Oh, hello. Okay, I see you. The client here, the sending server, can then begin to mail, specifying who's the sender, specifying who's the receiver. And for each of these comments, so mail from is a comment specifying the sender. Receipt to, reception to, receipt to. This is to specify the receiver. So for each of these comments, the receiving end sends back a status code, status phrase. Now, this is the handshake part, starting from here. When the client says DATA capital, that means, oh, okay, the content of the email is coming up next. And so these are the content. Do you like ketchup? How about pickles? Okay, a single line with a period means this is the end of the data. And this is defined in the SMTP protocol. Last is what? To close the connection, closure. Okay, so you see 3 phases: handshake, message transfer, and closure. So we can actually try to exercise telnet to a mail server and enter these: hello, mail from, receive to, data quit, and see how it goes. Shall we? Okay, let's try. Oh, wait, it seems to me the four screens all look the same as sides. As if looking at the storyboard. Uh-oh. Yeah, sorry about the lag. It seems the network today is not that good. Let me see. Yeah, it's no data. Oh boy. Oh boy, oh boy. Okay, give me a second. Let me just, well, yeah, I think lag is just really serious. Okay, so I'll handle this during the break. Okay, let's try. a terminal. Here. Is it big enough? All right. So 1 second. I have to. Is it enough? Hope so. All right. So, by the way, I don't have Telnet here, so I got it SSH to the. So I mean Telnet to the PA server. Network not good. I forgot. I don't even connect. Connect to host, poor connection refused. That's odd. Is it? Oh, yeah, you're right. No wonder. Who said that? Thank you, Kevin. Kevin, right? So you see, it's very challenging to do streaming and lecturing at the same time. Waiting forever. So I can see why the remote students having problem with the lags. Ouch. Okay, why don't we skip this part here? Okay, I can record a short video showing that you can actually telnet to a real mail server. See all these actual comments going. Okay, let me move the stuff back. All right, so final words about the SMTP. Okay, SMTP uses persistent connection, which means the connection remains closed for all the emails. Okay, this we already know. It's ASCII readable, and the last line is just one period. Okay, but be careful. Before the period, there's cartridge return and line feed, and afterwards another cartridge return and line feed. So these are the characters you don't really see on the screen, okay? But you have to show these followed by a period and these in order for the receiver to see, okay, this is the end of the data part. Now, comparing to HTTP. HTTP is mainly pull, downloading objects. SMTP is what? Pushing email out to the receiver. So, direction, opposite. But otherwise, ASCII code, there are always comments, okay? And there are always responses with status code and status line. Okay. In HTTP, there's one thing that's a little bit different from SMTP. Each object is encapsulated within its own response message. So if one page embeds 5 objects, for each object, we send one response. But in SMTP, one email can actually contain multiple objects. Okay, so that's a multi-part message. Do you send emails with just text? Yes, you do. Do you send emails with attachments? You do, right? Word documents, they are binary, not just text. So there's actually a separate standard there defining what this multi-part messages should be formatted. Okay. And that's not go to those detail, okay, but the basic form of a email message is like this. The header line contains, for example, sender, receiver, sender, of course, email subjects, okay, and then the actual content. But know that this to is not receive to. This from is not the mail from, okay? These are not the SMTP commands, okay? These are just the header lines in the message part of the email. So this is the protocol defining the format of these multi-part messages. Okay. Now, the second component of email application, so that was SMTP, really sending the emails back and forth between the mail servers. There's another level of hierarchy, isn't it? Which is to access emails. And timing is perfect, so let's take a break and we'll resume from, how do we access email? What are these protocols? POP3, IMAP, HTTP. And let me see if I can tune the streaming, the OBS a little bit to make the lag a little bit shorter. Okay, break. Hi.
Can you show me the comparison between HTTP and FTP again?
Sure. So, but it's probably easier if we just.
Yeah.
Take a photo.
I write this.
Okay. And remote students, I'll come back in a few minutes. Okay. Chances high that I'll be able to fix the wireless transmission situation today. Maybe next week I'll start by using the wire internet and see if it improves. I don't know why today suddenly the transmission is not working well.
So the two looks like basic.
Now that I think about it a little bit more, it's probably because of the bus on the motherboard is getting too busy. Because I'm getting a video input from my iPhone, so I can see that the motherboard is probably very very busy passing videos in and out. I think for that I might need a higher end laptop, okay, for the purpose if I want another input. So yeah, I guess I will need to upgrade the laptop, get a better laptop next time, and try to use wired, okay, network access. Now, in the meantime, yeah, I understand that the quality of the video is probably too bad. So I'll be uploading the segments of the videos pre-recorded. Okay, that should make up for the content that's missing. Now, in case there are any questions, feel free to ask, of course. Okay, so just in case, if you guys are still there, let me know if the audio quality is okay. In this case, I guess not, okay, because audio after OBS is encoded with the visual content. So, okay, well, just let me know whether it's just that the slides or the videos are not moving smooth. Okay, um, or both audio video. right, let's resume the lecture. So let's wrap up email. Okay, mail access protocol. So this is the last component, and this is speaking this from Bob to read Bob's email. This is to deliver and get the receivers, to get the, sorry. SMTP is to deliver emails and store emails to receiver server, okay? But it's really the mail access protocol there allowing Bob, the receivers, to get these emails. So there are multiple protocols, POP3 and IMAP. Both of them are still popular, okay? But nowadays, probably the most popular is HTTP. Okay, let me ask. Other than the NTU email addresses, okay, do you have a Gmail email address? Yes, you do. Do you have Yahoo Mail email? Yes. Hotmail? Also, okay. Which one you use the most? Gmail. Why?
Free.
It's free? But I thought Hotmail and Yahoo Mail are also free. No?
Clear interface?
Excuse me?
The interface is...
Get some free Google Drive space. Okay, so I ended up also using Gmail because for a while, NTU's mail servers are not that stable. I missed some emails and important. I get delays as well. Okay, so I changed to Gmail. Okay, but after NTU outsourced the email service to Google, then I returned. Okay. So you see, HTTP is now the most popular mail access protocol. But let's still take a look at POP3 and IMAP. Okay, so this is how POP3 works. Okay, very similar. There's a handshake or authorization phase, and then the real content. Okay, email content. So there are client side issuing comments like user, pass, and the server side returning with the status phrases. Okay, okay or error. So this is an example of someone going to, okay, someone is Bob. Bob here going to a server, checking email. So you see server here says, okay, I'm a POP3 server. Client here says, I'm user Bob. Server says, oh, okay, I see that you are in the database. Okay, you are one of the legit user. And then Bob send the password. Okay, hungry, okay. Server says, okay, you're through. Therefore, Bob here begin to check the list of emails he's received. So doing list here, this is another command. This lists all the emails, but list only the email number and the size of the email. So only when Bob types RETR, retrieve 1, then it shows the content of email 1. Okay. The end of the email is what? A period, right? With cartridge return and line feed before and after the period. Delete 1, remove that message. Check the second message, remove the second message. Last is to close, okay, closure. So client just simply say quit. So this is yet another comment. So list, retrieve, delete, and quit. From the server, you see a bunch of these okay, okay, or not okay, not okay. Again, read. This actually explains why we need IMAP. So POP3 here, okay. So we see in the example, what we do is we download the email and then delete it, okay, from the incoming box, mailbox. So if we do it this way, okay, Bob will not be able to reread the email if he changed from one client to another, right? Because the message already deleted from the server. If Bob goes to another client, use another client, for example, in the airport, checking from the public machine, Bob won't be able to read those emails anymore. Now, if we try to do it this way, okay, download and keep. We download the copy of the emails, but not delete the email. That also causes problem. We get copies of the messages on different clients. So this is when Bob go from one client to another client. The new clients, you don't see messages. This is also Bob going from one client to another client. So this client gets a copy of the message. That client gets also a copy of the same message. And for every client you go, you download a copy of the message. What's the worst is that you might find that some messages on this client and not on another client. You get confused. Okay, you don't know whether the sender didn't send it or you missed downloading it to that client. Okay, so confusion here, confusion here. That's because POP3 is a stateless protocol. Okay, after you retrieve the emails, okay, you can only leave it there or delete it. Okay. Therefore, IMAP, this is obviously a stateful protocol. Okay. What we do there with IMAP is, hey, we keep the files, keep the emails all on the server. Keep all emails on the server. Okay, and the user can try to organize these emails, creating folders, move some of the emails that are related to a particular folder. So emails will remain on the server, and IMAP is more like an email organizer. Okay. So it allows you to access these messages and allows you to organize the emails. Okay. So we keep the user states across sessions. Once you log in, IMAP will let the server know that you are this particular server and you have already built a. Oh, the quiz, this one is very brief. Oops, oopsie. Okay, pretend that you did not see that. So this quiz is very brief. If you recall, Alice, Bob, SMTP only go all the way to the receiver server. Between Bob and the receiver server, there is a mail access protocol. But why, right? Why can't we just push the emails all the way to Bob's user agent? Why not all the way? SMTP all the way to Bob. I mean, wouldn't this be nice, right? You don't have to bother doing the mail access protocol. Right? Bob getting the emails can organize all these emails locally. Why? Oh, right. Get your teammates, right? Discuss. Yeah, this one is not that obvious. Not that obvious. Oh, okay. Team 12 here already answered. Let's see. Since the client doesn't always, okay, so the client might not be online all the time, isn't it? How would the sending mail server know where to send? Yeah, so the delivery might not be successful anytime. What about you? Any other reasons? I mean, one. Very slow. Any more? Mm. Okay, so Kevin and I think Tim, let me see. 7? Yeah. It's saying that SMTP here is to mail, right? Deliver. And I think you're actually speaking along with Tito was saying, okay, you're delivering, okay, and the client might not be there. So pulling from the client side will be easier. From the user side will be easier. You want to deliver something. That's the keyword indeed. But who do you deliver to? We know what about at someschool.edu, right? Where is someschool.edu? You need to deliver to a particular IP address. Okay. Would that be easier to do than just bob at someschool.edu? What it takes? No. It might require more time to think about it. Yeah, I see this one is a little bit challenging, isn't it? Why not going all the way to Bob? Why not go all the way to Bob? Oh, there. Okay, team 3, Shu Wei. Still in back there. Saying, same as okay. To pull the map from. Oh, okay. IP address of Bob may. You think back. Why we go from POP to IMAP? Then you know. The reason that we go from POP3 to IMAP is what? We go from client to client, is it? These days, we have multiple clients, and we go from client to client. We are very mobile. It's just very hard to find. Oh, hey. Okay, so sorry to break the team discussion there. Yeah, so nowadays, we have multiple clients that we access to, and we'll move around. So that's why we move from POP3 to IMAP, and we are keeping the emails in the server and then never getting them down onto the local disk. Very good. Yumin is also getting it, probably. Yeah, SMTP is mainly just to send. And sending is challenging because you need destination. How do you know that? That's the first challenge to begin. The second challenge is, even if you know the IP address, it's changing all the time. You might not to the real receiver. Great discussion there. And now let's move on to the last topic today. DNS. Now, this is a huge topic. Okay? We're using it every day. In fact, all these other applications we've talked about so far, World Wide Web, email, FTP, all rely on DNS. If you think about it, it's actually a very general service that many of apps require. Great. I'm hearing the ticking sound from side. Okay, keep them coming, guys. Now, as I explain what it is for, it's the domain name system, DNS. What it does is to do this, to find the IP address from the name of the machine. For example, yahoo.com. Okay. We refer to a server with yahoo.com. But the thing is, I forgot my other microphone. Let me back here. Hey, sorry. Yahoo.com, where was I? Okay, so the name of the server, okay? But when browser is sending packets, see the HTTP requests, in the header, it needs to be an IP address, okay? Not yahoo.com, because routers, these cylinder machines, things the core of the internet, they don't recognize yahoo.com. So yahoo.com is easier for human beings to read. What is the IP address of the PA server? 140? 122.42.221. Is that correct? 112. Right? Even though we've already completed 3 PAs, we forget about it. Yeah, that's the issue. So domain name systems here is to translate, okay, from name that it's easier for human beings to memorize to the IP address that need to be used by the machines to forward packets. So this is very similar to this thing. Okay, each of us have a number of these identifiers. For example, I have a name. Do you have a name? Yes, you do. I have a social security number. Okay, so I think in Taiwan that's called the ID, right? National ID. You also have that number. How long is it? 10 digits. Okay, let me just say it. Pollys national ID number is F221133182. Okay. And my name is Polly Huang. Okay, now, what is my name? All right. What is my national ID number? Okay, sorry, I tricked you because I speak really, really loud with the national ID. Okay, but hey, it's harder to memorize, isn't it? Okay, so similarly, passport number. I don't even recall my passport number. So remembering numbers much harder than words, characters, readable characters. So we do need a DNS here to interface the users to the machines at the lower level. All right. So DNS service concerns this. How do you map the IP address and the name, and vice versa? Okay. And let me tell you in a nutshell. Okay, there are more details coming up. It's a huge distributed database system. How do we find, for example, what are named phone number? Okay. Do you remember your own phone number? You do? Oh, that's good for you. Okay. Okay, so from time to time I forget. So one time I was in a mall, right? So I forgot the chengpin. Okay, I forgot my member card. They asked me for the phone number, and it was like, what's my number again? Oh, do you guess what I do next? I asked a friend to call me myself. No, I actually look up my hide. So there's a distributed database with many of these name servers being connected with some sort of hierarchy. You're seeing a couple slides. It's actually quite elaborated. And you see also DNS in Chapter 2. DNS in Chapter 2, it's an application layer protocol. But you see also many other application layer protocols uses this service, right? It should be lower layer because all these application layer services need it. It's one of the core internet functions, in fact. So why implement it as an application layer protocol? Okay, so this DNS being at the application layer is really, really weird. Okay, but there's a very good reason for that. It's called keeping the complexity at the edge. Keeping the complexity at the edge. If you recall, in chapter 1, the applications right next to the users are all running on instance. None of these applications run on the routers in the core. Okay. And we like that because if we need to change it, we just need to change the end systems. We don't need to bother updating the routers in the middle. Similarly, DNS here being at the very end of the internet, not at the core, because chances high that we might need to update it quickly, okay, to keep internet going. Complexity at the edge. Okay. The DNS since day one is already complicated. Okay. We know it. Therefore, strategically, we put it all the way up into the application layer. Otherwise, it should be at the network layer. The network layer is the one assigning the destination IP address to the packet header. Therefore, we can forward it. Okay, so this is really weird. This will definitely appear in exams. Okay, maybe not in the second exam, but maybe a grad school entrance exam, for example. Complexity at the edge. Right. Now, you heard me saying, DNS is to provide mapping from host name to IP address, but that is not the only translation it does. Okay, it does also a number of other translations. Okay. One is this, host aliasing. Huh? What do I mean? So let me give you an example. .google.com. This is the host name of the Google search engine. Can you imagine that there's only one machine taking all the search queries? No, definitely not. Okay, this is actually an alias. Okay, for the real host name. Okay, because nowadays there are just so many machines, so many servers around, and each server needs a name. So we run out of the simple names. So they all come with some real host name, a little bit complicated, but we just refer them to google.com. And DNS service there would map from google.com, depending on where you are, to the real host name, the real search engine server. So that's called host aliasing. Okay, host aliasing. And then mail server aliasing, we were sending to Bob at someschool.edu, isn't it? Someschool.edu, that was not quite. Okay, if I just say google.com, is that a host? It is not. It's actually a domain name. All the machines will end with this. All the machines in Google end with this. So this is a domain name. This actually to characterize where this machine is from. Okay, which organization this machine belongs. So, Bob at someschool.com. Someschool.com is only a domain name. How do we know who's the mail server to contact? So we just finished talking about SMTP, right? So your mail server will need to find the receiving mail server. How? Call DNS. Try to find for this domain, what is the mail server's host name? And then find out for that host name, what is the IP address. So you need to do 2 queries to DNS, in fact. That's mail server aliasing. Also, low distribution. For Taiwan, the amount of search to www.google.com is very low. So we typically have only one machine, okay, one real host name to serve all the queries. But in US, particularly Silicon Valley, there are multiple of these real hosts associated with www.google.com. And every time you do DNS lookup, it actually rotates from the first real machine to the second and the third. So you can balance the search load among these 3 machines. It's enabled by DNS. Okay. Now, I've already said DNS is large, distributed, and hierarchical. Why not just one DNS server? Obvious reasons. It's a single point of failure. If you bring down that server, you bring down the entire internet. Unless you can memorize all the IP addresses in the world. No way. Traffic volume, yeah, that server, if you don't manage to bring it down, you can still, right, DOS attack to it. And the whole world is relying on it. Also, if there's only one machine, but hey, the internet is huge, right? The world is large. The delay to that server, at least from some part of the world, will be really long. The real disadvantage I see is more this, maintenance. If there's only one machine, you bring it down to update, the internet is also down. So, multiple machines, okay? Very obvious. Having just one doesn't scale in many ways. Finally, the hierarchy, okay? DNS being hierarchical. You see the hierarchy here? How many levels? Oh, one more level now. Email is 2 levels, but DNS, 3 levels. At the top, the root DNS server. The second layer, the .com DNS server, the .org DNS server, the .edu DNS server. So these are the top level domain server. And the top level domain server then can branch out to, for example, this is .com. Therefore, the .com DNS server is well connected to, for example, yahoo.com's DNS server, amazon.com DNS server, google.com DNS server, and so on and so forth. Okay? And it's really in these yahoo.com DNS server, amazon.com DNS server, google.com DNS server, we are storing these guys are. Okay, so if you're looking for a host, okay,